The assumption that contact point number 3 of the holding circuit is typically jumped to the coil is correct. This is a common wiring configuration for motor controllers, as it ensures that the coil remains energized once the start button is released. The fact that the motor came on without pushing the start button strongly suggests that contact point number 2 of the holding circuit was indeed jumped to the coil, rather than contact point number 3. There are some possible reasons for this error. Firstly, wiring mistake. The technician who wired the controller may have simply made a mistake. Secondly, internal fault. There may be a fault within the controller that is causing contact point number 2 to be energized incorrectly. Thirdly, mislabeled terminals. The terminals on the controller may be mislabeled or incorrectly identified. When taking the exam, reread the instructions carefully to ensure that you understand the expected wiring configuration. If possible, inspect the controller visually and see if you can identify any obvious wiring errors. If you are unsure about the wiring, ask the proctor for clarification. They may not be able to provide specific guidance, but they can confirm the expected behavior of the controller. If you have access to a continuity tester, test the controller to verify that the coil is connected to contact point number 3 of the holding circuit. Follow a methodical approach. Disconnect the power and carefully wire the controller according to the instructions. Double-check your connections before energizing. It is important to be aware of the potential for wiring errors and to verify the connections before energizing any electrical equipment. If you encounter an unexpected issue, do not hesitate to seek help from a qualified technician or the proctor. Stay calm and focused during the exam. Troubleshooting electrical issues can be challenging, but with careful attention to detail and logical reasoning, you can overcome them. Motor controllers use a holding circuit, also known as a maintaining circuit or a latching circuit. This circuit is designed to keep the motor running even after the start button is released. This is typically achieved by using a normally open auxiliary contact on the motor starter or contactor that is wired in parallel with the start button. When the start button is pressed, it energizes the motor starter coil, which closes the main contacts to start the motor and also closes the auxiliary contact. Once the auxiliary contact closes, it provides an alternative path for the current to flow to the coil, bypassing the start button. As a result, the coil remains energized even after the start button is released, and the motor continues to run. The holding circuit is essential for maintaining continuous operation of the motor without requiring the operator to hold the start button continuously. The most common way to stop the motor is by pressing the stop button, which interrupts the current flow to the coil, causing the main contacts and the auxiliary contact to open, thus stopping the motor. The typical wiring configuration involves the stop button, motor starter coil, and an auxiliary contact of the motor starter. The start button is a normally open momentary contact switch. When pressed, it allows current to flow through to the motor starter coil. The stop button is a normally closed momentary contact switch. When pressed, it interrupts the current flow to the motor starter coil. The motor starter coil is an electromagnet that, when energized, closes the main contacts to start the motor and also closes the auxiliary contact. The auxiliary contact is a normally open contact that is mechanically linked to the motor starter coil. When the coil is energized, the auxiliary contact closes. The holding circuit is a parallel circuit consisting of the start button and the auxiliary contact. The start button allows current to flow to the coil initially, and the auxiliary contact maintains the current flow after the start button is released. Understanding the function and components of a holding circuit is crucial for troubleshooting motor control systems and ensuring safe and reliable operation of motors. Always disconnect power before working on any electrical equipment, and follow proper safety procedures. When troubleshooting a motor controller, a systematic approach is essential to quickly identify and resolve the issue. Firstly, start by visually inspecting the controller for any obvious signs of damage, such as burnt wires, loose connections, or damaged components. Look for any signs of overheating or arcing, which could indicate a short circuit or insulation failure. Secondly, check the input voltage to the motor controller to ensure that it is within the specified range. Use a voltmeter to measure the voltage at the line terminals and compare it to the voltage rating of the controller. If the voltage is too low or too high, it could cause the controller to malfunction. Thirdly, verify the continuity of the control circuit. Use a multimeter to check the continuity of the start and stop buttons, the motor starter coil, and the auxiliary contacts. Ensure that the start button is normally open and closes when pressed, the stop button is normally closed and opens when pressed, and the motor starter coil has the correct resistance. Fourthly, examine the wiring connections to ensure that they are secure and properly terminated. Loose connections can cause intermittent operation or complete failure of the motor controller. Tighten any loose screws or terminals and replace any damaged wires. Fifthly, test the motor starter. Energize the control circuit and observe the operation of the motor starter. Ensure that the starter engages and disengages smoothly and that the main contacts close and open properly. Use a multimeter to measure the voltage across the motor terminals to verify that the motor is receiving the correct voltage. Sixthly, check the overload protection devices. Motor controllers typically include overload relays or circuit breakers to protect the motor from overcurrent conditions. Verify that the overload protection devices are properly sized for the motor and that they are functioning correctly. Reset any tripped overload relays or circuit breakers and monitor the motor current to ensure that it is within the rated limits. Seventhly, use a systematic approach to isolate the problem. If the motor controller is not functioning correctly, disconnect the motor and test the controller independently. This will help to determine whether the problem is in the controller or in the motor. Eighthly, consult the manufacturer's documentation. Refer to the motor controller's manual for troubleshooting tips, wiring diagrams, and component specifications. This information can be invaluable in diagnosing and resolving complex problems. Finally, document your findings. Keep a record of all the tests and measurements you perform, as well as any repairs or adjustments you make. This will help you to track your progress and identify any recurring problems. By following these steps, you can effectively troubleshoot motor controllers and ensure the reliable operation of your motor-driven equipment. Electrical safety is paramount when working with motor controllers and other electrical equipment. Firstly, always disconnect power before working on any electrical equipment. This is the most important safety precaution you can take to prevent electric shock. Use a properly rated disconnect switch or circuit breaker to de-energize the circuit. Secondly, verify that the circuit is de-energized. Use a voltmeter to confirm that the voltage at the terminals is zero before touching any wires or components. Test the voltmeter on a known live circuit before and after testing the de-energized circuit to ensure that it is functioning correctly. Thirdly, use appropriate personal protective equipment or PPE. Wear safety glasses, insulated gloves, and appropriate clothing to protect yourself from electrical hazards. Avoid wearing jewelry or other conductive items that could come into contact with live circuits. Fourthly, follow lockout/tagout procedures. When working on electrical equipment, follow established lockout/tagout procedures to prevent accidental re-energization of the circuit. Place a lock and tag on the disconnect switch or circuit breaker to indicate that the circuit is being worked on. Fifthly, be aware of arc flash hazards. Arc flash is a dangerous electrical phenomenon that can occur when a short circuit or other fault creates an arc of electricity. Arc flash can cause severe burns, blindness, and even death. Wear appropriate arc flash PPE when working on or near energized electrical equipment. Sixthly, maintain a safe working distance. Keep a safe distance from energized electrical equipment to avoid accidental contact. Use insulated tools and equipment to perform tasks safely. Seventhly, never work alone. Always work with a partner or notify someone of your intentions when working on electrical equipment. This way, if an accident occurs, someone will be available to provide assistance. Eighthly, inspect tools and equipment regularly. Check your tools and equipment for any signs of damage or wear before using them. Replace any damaged tools or equipment immediately. Ninthly, follow manufacturer's instructions. Always follow the manufacturer's instructions when installing, operating, or maintaining electrical equipment. This will help to ensure that the equipment is used safely and effectively. Finally, stay informed and trained. Keep up to date on the latest electrical safety standards and practices. Attend training courses and workshops to improve your knowledge and skills. By following these electrical safety precautions, you can significantly reduce the risk of electrical accidents and ensure a safe working environment. Motor controllers are used in a wide variety of applications to control the starting, stopping, and speed of electric motors. Firstly, industrial machinery. Motor controllers are used to control the motors that drive pumps, fans, compressors, conveyors, and other types of industrial machinery. Secondly, HVAC systems. Motor controllers are used in heating, ventilation, and air conditioning, or HVAC systems to control the motors that drive fans, blowers, and compressors. Thirdly, water and wastewater treatment plants. Motor controllers are used to control the motors that drive pumps, mixers, and other equipment used in water and wastewater treatment plants. Fourthly, elevators and escalators. Motor controllers are used to control the motors that drive elevators and escalators, providing smooth and safe operation. Fifthly, mining and construction equipment. Motor controllers are used in mining and construction equipment such as cranes, excavators, and drilling machines. Sixthly, renewable energy systems. Motor controllers are used in wind turbines and solar power systems to control the motors that drive generators and other equipment. Seventhly, electric vehicles. Motor controllers are used in electric vehicles to control the motors that drive the wheels, providing precise control over speed and torque. Eighthly, robotics. Motor controllers are used in robotics to control the motors that drive the joints and actuators, enabling precise and coordinated movements. Ninthly, packaging machinery. Motor controllers are used in packaging machinery to control the motors that drive conveyors, fillers, and sealers, ensuring efficient and reliable packaging operations. Finally, printing presses. Motor controllers are used in printing presses to control the motors that drive the rollers, feeders, and cutters, providing precise control over the printing process. These are just a few examples of the many applications where motor controllers are used. Motor controllers play a critical role in ensuring the efficient and reliable operation of electric motors in a wide range of industries. The National Electrical Code, or NEC, provides comprehensive guidelines for the safe installation and wiring of electrical equipment, including motor controllers. Firstly, Article 430 covers motors, motor circuits, and motor controllers. This article provides requirements for motor overcurrent protection, motor disconnecting means, motor control circuits, and motor overload protection. Secondly, Section 430.52 covers motor overcurrent protection. This section specifies the maximum size of the overcurrent protection device, such as a fuse or circuit breaker, for motor circuits. The overcurrent protection device must be sized to protect the motor and the motor circuit conductors from overcurrent conditions. Thirdly, Section 430.102 covers motor disconnecting means. This section requires that a disconnecting means, such as the switch or circuit breaker, be provided to disconnect the motor from the power supply. The disconnecting means must be readily accessible and capable of being locked in the open position for safety during maintenance and repair. Fourthly, Section 430.110 covers motor control circuits. This section provides requirements for the wiring and protection of motor control circuits, including control transformers, control circuit conductors, and control circuit overcurrent protection. Fifthly, Section 430.125 covers motor overload protection. This section requires that motors be protected from overload conditions by means of overload relays or other approved devices. The overload protection device must be sized to protect the motor from overheating due to excessive current draw. Sixthly, Article 310 covers conductors for general wiring. This article provides requirements for the size, insulation, and ampacity of conductors used in electrical wiring. Seventhly, Table 310.15b16 provides the ampacity of insulated conductors. This table specifies the maximum current carrying capacity of conductors based on their size, insulation type, and ambient temperature. Eighthly, Article 250 covers grounding and bonding. This article provides requirements for grounding electrical systems and equipment to protect against electrical shock and to provide a path for fault current to flow back to the source. Ninthly, Section 250.122 covers equipment grounding conductors. This section specifies the size of the equipment grounding conductor based on the size of the overcurrent protection device in the circuit. Finally, Article 110 covers general requirements for electrical installations. This article provides requirements for the quality of workmanship, the identification of electrical equipment, and the proper use of electrical equipment. These are just a few of the many NEC requirements that apply to motor controllers and motor circuits. It is important to consult the NEC and other applicable standards to ensure that electrical installations are safe and code compliant. Understanding the function and operation of a motor starter is essential for troubleshooting motor control systems. Firstly, the motor starter is an electromechanical device that provides a safe and reliable means of starting and stopping an electric motor. It typically consists of a contactor, overload relay, and other control components. Secondly, the contactor is a magnetically operated switch that connects and disconnects the motor from the power supply. When the contactor coil is energized, it closes the contacts, allowing current to flow to the motor. When the coil is de-energized, the contacts open, disconnecting the motor from the power supply. Thirdly, the overload relay is a protective device that protects the motor from overcurrent conditions. It monitors the current flowing to the motor and trips if the current exceeds a predetermined level. When the overload relay trips, it de-energizes the contactor coil, disconnecting the motor from the power supply. Fourthly, the control circuit is used to control the operation of the motor starter. It typically includes start and stop buttons, selector switches, and other control devices. The control circuit energizes and de-energizes the contactor coil, controlling the starting and stopping of the motor. Fifthly, the motor starter provides overload protection. The overload relay protects the motor from damage due to overcurrent condition. Sixthly, the motor starter provides undervoltage protection. Some motor starters include undervoltage protection, which de-energizes the contactor coil if the voltage drops below a certain level. This prevents the motor from restarting automatically after a power outage, which could damage the motor or the connected equipment. Seventhly, the motor starter provides phase loss protection. Some motor starters include phase loss protection, which de-energizes the contactor coil if one of the phases of the power supply is lost. This prevents the motor from operating in a single-phase condition, which could damage the motor. Eighthly, the motor starter provides short-circuit protection. The motor starter is typically protected by fuses or circuit breakers, which provide short-circuit protection. These devices interrupt the flow of current in the event of a short circuit, preventing damage to the motor and the motor starter. Ninthly, the motor starter provides remote control. The motor starter can be controlled remotely using push buttons, selector switches, or other control devices. This allows the motor to be started and stopped from a remote location. Finally, the motor starter provides automatic control. The motor starter can be controlled automatically using timers, sensors, or other control devices. This allows the motor to be started and stopped automatically based on predetermined conditions. Understanding the function and operation of a motor starter is essential for troubleshooting motor control systems and ensuring the safe and reliable operation of electric motors.